Yes, that's right. So we've heard a bit about the motivation for this already yesterday. Space leaks are quite scary, right? You write these applications, they go out, they use memory, they use too much memory, your servers crash, everybody's unhappy, it's horrible, you're terrified. And part of the issue is like, you get these space leaks, and then they're quite difficult to analyze. Matt touched on this yesterday, that you need to have these skills, looking at profiles, understanding semantics, and that's kind of like our first port of call for talking about these issues. And in this talk, I want to introduce a way of doing this that doesn't really require you to understand these things in depth. So I have this idiom, stateful or lazy, that will help guide us to know when we want to be very strict. And this is quite important in terms of not being strict all the time, because when you're doing performance analysis, it's quite tempting to kind of do this shotgun type of approach of, oh, I've had space leaks because of thunks, so let's just get rid of all thunks. So this is about specifying when we want to be strict. And I've made this tool for allowing you to enforce these things. So what is a space leak? A space leak is when we use more memory than necessary. So primarily we care about when the duration or like the lifetime of objects is more than necessary. So again, quite similar to Matt, I've got these notions of like memory invariance type things going on. So here we have a graph of the memory usage of an application. We could imagine that it's like a web server or maybe HLS. You've got your necessary memory usage here, and it's got a baseline, right? And there's these two spikes that correspond to maybe handling a web request or compiling a module or something, right? So memory usage goes up when you do the request, and then it goes down when you're done, right? You don't need to hold on to things anymore. Now, shock horror, the actual memory usage of our application is more than what is necessary, right? So there's this bounded case, and in the bounded case, the shape is quite similar. So it does differ within the second spike, right? It goes up, but it doesn't come down immediately during handling the request. Maybe you're parsing some code and you're keeping it around for the entire request, but you don't really need to. But very importantly, it does go down at the end. And these types of things are quite annoying and they can be problematic, but they're very unlikely to crash your application because you have this notion of it being bounded by handling the request. Memory is released after this specific event, and you can reason about that. In the unbounded case, memory is never released, right? There's no event where you can say, okay, this is when the memory will be released. And that's particularly concerning. Now, space leaks have many different causes. Laziness is just one of them, but it is the one that gets a lot of focus and is also what I'm going to be talking about, so I'm making this problem worse in some ways. But there's also lots of other things, right? You could be using inappropriate data types, right? We use lists quite a lot, but if you have a lot of data, lists aren't really the right choice. You might want to use vector, right? That only has a constant overhead for the elements, whereas list has an overhead for each element. You might have function closers causing space leaks in a very similar way to thunks. You might have excessive stack usage if you use too many lightweight threads. And I'm sure there's many more that I haven't thought of, right? So let's focus in on laziness a bit, right? Laziness means we only do work when it's demanded. But if work isn't demanded, we need to represent this future work in some way. And we do that through a thunk. A thunk has a small cost and also has the cost of keeping alive all the data you need to do the work in the future. And that's kind of how we get these space leaks, mostly by keeping alive data rather than the cost of the thunk itself. So let's look at an example. This is like the classic example of a space leak. We've got this thing that's summing up things, and we're using the lazy full del, which I'm sure all of us here know not to do, but we've written this code, and we're expecting it to have constant space usage, but it has linear space usage, which is not great. So what's happening here? We're building up a chain of thunks as we're executing this, right? We see an element, we're like, okay, let's sum this up, but we don't need to do that right now, so we put it on the chain. When we reach the end, we're like, oh yeah, we do actually care about the thunk, and then we run down this chain and squeeze them all into a value. And the solution here is to just use the strict fold, right? We're just adding a bit of strictness, and that's fixing it here. One thing to know about this is, like in this example, it's very simple. And if you turn on the optimizer might just figure it out and do this for you. But we can't do that in general. The other thing is, this is a bounded example because we're bounded by processing this list, right? And if the list is small, maybe you don't really care. If the list is huge or infinite, right? Well, then you really care. But if you're doing this on infinite list, you won't terminate anyway. So we don't really care. Now, let's look at a bit more of a practical example. Let's put ourselves into the headspace of like an industrial programmer. You've been tasked with calculating the average of a list. And you're a very clever programmer, so you've figured out how to do it with one traversal, all right? But this example has a space leak. So what you're doing here is you have this state, and as part of it, you have the running sum, and you have the running length. And as you're walking along the list, you're adding in the value to the sum, simple enough. You're adding into the length, 1 to the length, right? And at the very end, you divide. And this is quite a nice way to do it. And you've learned from the previous lesson. You're using th-deepstrict, but you still have a space leak. And why is that? Because the values in your state accumulate thunks. The overall state doesn't. That's forced. But the values inside it still have the same issue. And this shows that just using top-level strictness isn't enough, right? If you want to completely eliminate thunks, what you want is deep strictness. And in technical terms, what you want is normal form, not weak-head normal form. But if you don't understand what that is, don't worry about it, right? So the solution here is to add these bang patterns, which we've heard a bit about before. So you need deep strictness. And these two examples are both bounded, right? Because you're just processing this list. But let's look at an unbounded example. Here, your product owner comes back to you and is very impressed with the previous stuff and asks you to make a web server that does the same thing. So you've removed your bang patterns, and now you have some global state, right? You have this IRF, and then you have two handlers that are plugged into your web server stuff, and it's just calling the stuff from before. You add a number into your set, and then you do the step function before, and maybe you output the average at some point. And what's very tricky about this example is most of the time, right, users will just add a couple of things, get the average. The space leak isn't all that noticeable. But once in a while, you'll have a user that adds a bunch of numbers, and that will grow this chain. And that's when you get these issues. So it can be quite difficult to detect these in production. And I should also note that like the IRF here isn't crucial, right? You could just have it as a recursive function, and that's how the state gets passed around. So in these examples, we've seen two things interacting. We've seen laziness, but we've also seen statefulness. And that's a really important thing, because an immediate reaction to these things is saying, okay, laziness has caused these problems for us. Let's just get rid of all laziness. Let's turn on the strict language extension, make everything strict, which also doesn't work, but anyway. But statefulness also plays a key role, right? You're building up this chain of thunks, and the chain is being built by the statefulness. Those are your state values. And being stateful is exactly having a sequence of values over time that are dependent on each other. So when these two things interact is when you get these space leaks. And kind of the severity of the space leak is tied up with the level of statefulness. If you have global state, you tend to get unbounded laziness, whereas if you have state local to something, then that will be bounded by that something, right? If you have stuff that is local to handling a web request, that state gets thrown away, and then any space leaks would also get thrown away. And yeah, let's just focus in on statefulness a bit more, right? We've seen a couple of examples, but let's be clear about it. So it's not just the state monad. The state monad is one form of statefulness, but we've also got recursion, right? When you recurse, you have this recursive argument, and that is a form of statefulness. Every time you recurse, you're using that same value, and you have the potential for building this chain. Also things implemented in terms of recursion, right? Like folds, if you're imperative-minded loops, and then also mutable state, right? That's another form of statefulness. And we tend to use the strict versions when updating them, but it's very important to also be deep strict about the data in them. So then my proposal to you is that you should be stateful XOR lazy. I'm not saying stateful NAND lazy because if you're not forced, you should just be lazy. So it's stateful XOR lazy. So yeah, and for us, this is quite an easy choice most of the time because you just shouldn't be stateful. We don't like being stateful anyway, so we should just be lazy. But if we are forced to be stateful because statefulness is unavoidable, then we should be deep strict. And a thing as well, I think, is that when you have a code base that has a lot of stateful stuff, that's normally a reflection of architectural issues, right? So maybe you have a lot of state in it, and maybe the answer to that is just to move it out into a database. Because if you are holding on to a huge amount of state, it's very likely that you end up implementing a database, and maybe that's not something you want to do. And if you do have state, make it as local as possible, which is just like general advice as well, right? You really don't want global state because of all the issues associated with it in terms of reasoning about your code, but especially space leaks and reasoning about these space leaks in global state. So we should make it deep strict, right? And there's two ways you can make things deep strict, right? You can make your code deep strict, but from the start we said we're not going to reason about our code here. That's too difficult right now. So we're just going to focus on our data types, because that's quite a nice way of encoding invariants in our code, is by making those invariants be expressed in our data types. So what is a deep strict data type, right? It's kind of this recursive definition, and it's kind of what you'd expect. You have bangs on all of your fields in all of your constructors, right? But then also the types of those fields are themselves deep strict. So this goes all the way down. And like you have to be careful with things like just, right? Because that is something that comes from base, and it's lazy. And you can't really control that. Like in Andreas' talk, we heard mention of this thing of having a bang inside the just, so that would be really nice. But yeah, so you want to enforce this. And that's why I wrote a library. I wrote it while working at Traxxas, and they let me open source it. And it's implemented using TemplateHaskell. What it does is kind of like walks down your data type and checks that everything is strict and all of your types are strict all the way down, right? And it's actually not all that trivial, mostly because of the interface of TemplateHaskell is a bit awkward, and we return the strictness of things in a confusing way. And a lot of that's been upstreamed into th abstraction, which is quite nice. And this is quite like an industrial tested library. We allow things that you would expect in an industrial setting, like overriding the inferred strictness of types, because this can actually infer the strictness of most types, including like fancy built-in unboxed, unlifted types, thanks to TemplateHaskell. But you want to often override things like some data types have internal laziness that you want to support and not warn about. And it also lets you write golden or ratchet tests. Yeah, go on.
Do you support GADTs?
Yeah, I've not tried, but I think so. Sorry?
Please repeat the question.
Oh, do we support GADTs? I think so, but I don't think I've ever tried. There's a couple of things that we don't support. I don't think we support type families very well, but that's just, I haven't got around to implementing it. And yeah, so we support golden or ratchet tests, right? So you write the output of all the lazy fields in your type into a file, and then you can check that into your source control, and that's a really nice way of kind of working away at this incrementally without just failing outright. And then you can see if anybody adds a new lazy field, maybe some of those lazy fields are okay and you don't care about them, and then it's okay to have them in there, and it's kind of a way of documenting stuff as well. So here is an example from our lazy state type. So you say this assert deep strict thing, and it gives you back a nice little pretty printed thing to say, well, it isn't deep strict. Why? Well, you have this field and it's lazy, and you have this field and it's lazy. And the output is pretty nice and okay, even for quite huge types where things are embedded quite deeply and stuff like that. So it deals with the performance is okay, and deals with repeated types, so it doesn't have exponential things like that. So yeah, then, right, you've seen that these things are need to be strict, but how do you actually implement that? And for that, you need to have strict types and strict data types. And because the ones in base and standard libraries aren't necessarily strict, there's these packages that fill the gap. So there's the strict package that has strict maybe and some other things. There's strict containers, which has strict versions of all the containers. And there's also this quite nice strict wrapper thing by Tom Ellis that kind of is a type family that sends a lazy type to its strict variant. And he's also written about why we should encode these things in types, which is quite good. One thing we do have is what I call the strict vector problem. Basically, I don't think we as a community have settled on a good strict sequence type. Lists aren't good. Once you make them strict, all of the big O stuff goes out the window. Vector isn't good because you end up copying a lot. So you really want something that's like got good asymptotics on everything, but is also strict. And I'm not quite sure if we're there yet. And in general, you end up with kind of this bizarre world where you have your normal data types and then you have a strict variant of all of them. And that is a bit awkward, and I wish we could do better as a community there. But also, it being a bit awkward kind of forces you not to do this too often, so you kind of go the lazy route rather than the stateful one. So I have some slides about alternatives. So one thing you could do is try to use DeepSeek everywhere, right? So that's how you enforce things being in a normal form. You just call this stuff from DeepSeek to do that. And I've found that is very error prone. You end up giving custom instances because it's too expensive, and then you don't end up actually deep seeking everything. And if you want to deep seek everything, it ends up being O of n, right? Because you're traversing the entire thing. You don't have knowledge about what's being evaluated already. And if you're doing this every time you're updating like a big global state variable, that's really, really expensive. And then making it more refined is then quite difficult to reason about. So I don't think this is a great approach. Yeah, Ben?
It seems like that's a great sort of interaction with your package, though, right? I mean, you could check your th package could check to make sure that the DeepSeek either does feel as strict,
yes,
or the DeepSeek instance, the NF data instance that you give it, is strict in that. I mean, that would be another mode of operation, I suppose. That might be a
that would be excellent. So Ben mentioned that there's potential synergy here between my package and DeepSeek, where we could give, we could use our knowledge to say, well, this bit is deep strict, so we don't have to evaluate it. And I think that would be good. I could just output a type class instance for NF data that does that. But because I don't really use NF data that much in these scenarios, I've never had reason to, but a PR would be welcome. The other kind of alternative is using nothunks. So this is a library by Edsco de Vries, and I kind of think about it as writing unit tests about laziness, right? You create a scenario, and then you have an object, and you look at it, and you're like, are there any thunks in here? And I think this is a great approach, and it's great, especially for data types where you want to enforce these things, but the data type itself, data structures, where you want to enforce certain strictness invariants, but the entire thing isn't strict for performance reasons, right? I think it works great there, but I don't think it works well in these big stateful scenarios, because the thing with stateful code is the state space grows really quickly. And so it's very difficult to have good test coverage because you just end out a couple of points in the database and you're like, okay, there's no thunks there. And you could imagine, like in our scenario with the web server thing, you just be testing certain sequences and you wouldn't have the issue there because you're getting the average and that's forcing things for you. So I think it is a very helpful library, but putting things in data types as an invariant is just more robust. And that's kind of, now I'm going to conclude, right? So you have this thing, statefuls or lazy, right? If you have state in your code, well, maybe try to avoid it. if you still have state in your code, make it deep strict. How do you make it deep strict? With my th-deepstrict library. It tells you where you're not being strict enough, and then there you can enforce it with using these data structures and just adding bang patterns or whatever. And one thing here is that this is still somewhat of a blunt hammer, but it's a lot better than just making everything strict. I wish we had better tooling around just looking at the core and figuring out these invariants there. But until then, I think this is quite a good way of doing these things. Cool. So do we have questions?
Let's first thank the speaker.
Okay. Yes?
So what do you do about IRFs?
Yeah, so, well, so the question is, what do you do about IRFs? But do you mean, like, if you have a data type and it's got an IRF in it? Well, what you kind of want to say is the thing inside the IRF is also deep strict. So with any type of mutable reference in your data type, we can kind of generalize it like that.
You can't, you have no guarantees about the way that the IRF is written.
I see. Yes, that's a good point. Yeah, you don't have guarantee. The response was we don't have guarantees about how the IRF is written. You want a strict wrapper around the IRF. Yes, that only exposes an interface where you do it strictly. Yeah, you definitely need that. Yes.
So yeah, this sounds really awesome for debugging your code. But if we step back a bit and think about when you want to model something that's lazy, wouldn't it theoretically be better to have a way to model it as a co-inductive data type?
Yeah. So the question was like, wouldn't it be better to use co-inductive data types when you want when you kind of have like inherent laziness? Yeah, yeah, definitely. I think that would be really neat. I'm not sure like how well we support those things, but I would love to have stuff like that and just more co-data stuff in Haskell in general. I think that would be great.
So I don't totally understand your critique of no thumbs.
Yeah.
So like in your web server example.
Yeah.
Wouldn't it be just a matter of saying, like, you know, after each when you're testing it, after each request, check the global state with no hunks, and that's it. And like, if there are any, then you fail, and if there's none, you carry on.
Yeah. Okay. The question was with what uncertainty about the critique of no thunks. Couldn't we just, if we have this invariant where we want memory usage to go down after each web request, can we just test things with no thunks after each web request? And see if that's the case. Well, it depends on how many types of web requests you have, right? And how complex they are. You can have completely different behavior based on the arguments. Maybe stuff isn't triggered unless a different code path is executed. Maybe you've got configuration flags and feature flags, and and you end up with a huge state space, and it becomes unreasonable to test every single configuration with unit tests. So yeah, that's the thing. Yeah. Yeah, go on.
Is it not a bit extreme to say that state should always be strict? Aren't there some data structures that rely on laziness to get good asymptotic?
Yeah, so the question was, should state always be strict? Sometimes data structures rely on laziness for good asymptotics. Yes, and that's fine. You can just say, override that and say, well, the internal laziness in this data structure is fine. But you do want to say that the keys and the values of the data structure are still strict. So you can kind of say stuff like that. You want to have these kind of inferences based on the type variables.
Okay, so one final question. All questions have been answered.
Nice.
That's done.